Kepler's final law. A planet's orbit obeys this relation. So this right here, p squared equals a cubed, is Kepler's third law. And again, don't worry if this doesn't make sense yet. This is actually, just like law number 2, saying something very simple, okay? So Kepler's third law is just p squared equals a cubed. However, if I went up to a little kid and said, hey guys, p squared equals a cubed, that little kid's not going to know what I'm talking about, right? So let's figure out what this really means, okay? Let's try to do this kind of quick. First of all, we actually already said what lowercase a was. Way back on law number 1, I said a was the semi-major axis. But I also said that that represents the average distance from that planet to the sun. So this right here, this side of the equation, is talking about how big the orbit is, okay? And then over here, on the p side, I've got p equals the orbital period in years, okay? So let's check this out. Here we go. Can anybody figure out in more like layman's terms, in like regular language, what is orbital period? If I talk about the orbital period of a planet, what am I talking about? What does orbital period mean, if you were to take a guess? Somebody said, yes, finally some math. Exactly. Woo, yay, math. We got excited. Yeah. That's right. Orbital period is how long the planet takes to orbit the sun. So A is talking about the size of the orbit, and P is how long the orbit takes. Okay, so let's check it out. In astronomical units, what is the average distance for the Earth? How many astronomical units is the Earth away from the sun on average? Don't overthink this. We actually just said it a little while ago. How many astronomical units is the Earth away from the sun? 1. In fact, that's how an astronomical unit was defined, right? So if we were going to do this law for Earth, we would plug in a 1 right here. And 1 cubed is just 1 times 1 times 1. So this side would just be 1, right? So 1 times 1 times 1 is 1, all right? Now, check this out. What's the orbital period of the Earth in years? What's the orbital period? How long does it take the Earth to go around the sun in years? 1, right? So if we plugged in a 1 right here, 1 squared is just 1 times 1. So if we did this for Earth, it would say 1 equals 1. Yay! The law works for Earth. But the important thing here is that this relationship works for every planet. If you know how big the orbit is, you know how long it takes to go around the sun. And if you know how long it takes to go around the sun, you can calculate how big the orbit is, okay? But even then, that's not really telling us what this really means, okay? So here's the next question. To help us understand what this really means, let's look right here. It's going to mean 2 basic things. If we increase this side, because we got this equal sign right here, the other side has to grow too. So one of the things this law is saying is that if you've got a bigger orbit, it takes more time, okay? If you have a bigger orbit, it takes more time for that planet to go around the sun. Some people are doing some calculations down there. Don't worry about doing any calculations right now. Don't worry about any of that. So yeah, one thing that this law is saying is bigger orbits take more time, smaller orbits take less time. Is that surprising? No. But there's one other more important thing that this law is saying. Check it out. Here's a hard question. See if any of you guys can answer this hard question. Here we go. Does 2 equal 3? Does 2 equal 3? When I said it was a hard question, I didn't mean be scared. Nope. 2 does not equal 3. Good job, guys. You guys smart. You smart. Yay. So, what does it matter that they've got a different number on each side here? What that tells us is that these things don't increase at the same rate. Because A is to the third power and P is to the second power, when you increase them, they don't increase at the same rate. So what does this mean for our planets? Okay, check this out. Our orbit has 1 AU, and it takes us 1 year. Mercury, we said, had an orbit with 0.4 AU, right? Mercury had 0.4 AU. So it seems like that should take 0.4 years, right? If Mercury's orbit is 0.4 the size of ours, it seems like it would take 0.4 years, but it doesn't. Mercury only takes 0.25 years. So Mercury's orbit is 40% the size of ours, but it only takes 25% of the time. What does that tell us about Mercury compared to Earth? If Mercury's orbit is 40% the size of ours, but it only takes 25% of the time, what does that tell us about Mercury compared to Earth? It tells us exactly. In a goofy way, somebody just answered that Mercury, don't try to do math. Don't worry about the math. If Mercury's orbit is 40% the size of ours, but it only takes 25% of the time, that means it must be going faster than us, right? It must be going faster than us if it takes less time to do than it should, right? So Mercury is very, 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 very fast, right? In fact, that's how Mercury got its name. In fact, some of you might know that the planets are named after Roman gods, and Mercury is the Roman name for Hermes, the god of speed. So Mercury got its name because it's a very fast-moving planet. It's the fastest moving, right? On the other hand, Neptune's orbit is 30 times the size of ours, okay? Neptune's orbit is 30 AU. So check this out. It seems like it should take 30 years for Neptune to go around its orbit. But if you can see the pattern that I'm trying to build up to here, would Neptune take 30 years? No. Is Neptune going to take more than 30 years or less than 30 years to go around the sun? If you can figure out what the pattern I'm trying to talk about is. See if you can get it. So Mercury was moving faster than us. Neptune, it turns out, takes 186 years to go around its orbit. Neptune takes 186 years to go around its orbit. It's 30 times the size, but it takes 186 years to go around it, 186 times the time. So what does that tell us about Neptune? What's true about Neptune? Yeah, Neptune's a slow boy, right? Neptune's a slow boy. So yes, we finally have put it together in a very complicated way. What Kepler is trying to say here, what Kepler's third law really says, is that the bigger an orbit is, the slower the planet moves, okay? The bigger an orbit is, the slower the planet moves, all right? So in fact, here's a graph that shows distance away from the sun right here versus their period over here. How long it takes, or their orbital speed. Sorry, this is the orbital speed right here. And as you see, as you go away from the sun, the planets get slower and slower and slower and slower. Which, yeah, as some people have pointed out, that means that Kepler's second law and Kepler's third law are both saying that there's something about being close to the sun that makes you fast. Okay? There's something about being close to the sun that makes you fast. Okay. So, here we go. Yeah, somebody actually mentioned gravity right here. Here's something super important. Did any of these laws say why these things happened? Okay? Did any of these laws say why these planets go faster when they're closer to the sun? Was any of that mentioned? No. He didn't mention gravity at all. He didn't mention any explanation for why the orbits do this. Why didn't he mention that? It's because Kepler didn't know why. He didn't know why planets went faster when they went closer to the sun. He just watched them and saw that they did. And he's explaining what the orbits do, not why. That's why these are called laws here, okay? Now, check this out. Check this out. Here we go. He actually thought that the sun might be a giant magnet and that the planets were attracted to that magnet. And that's why the orbits did this, right? Magnets, how do they work, right? But he never came up with a reason. Okay, now, check this out. Did people like Copernicus's idea? No. So then Kepler comes along and says, hey guys, you know that idea you didn't like? I took it and added more math to it. I tweaked it a little bit, made it a little bit more complicated and a little bit more mathy. Did that convince everybody? Did that convince everybody that they wanted to believe this new idea that everything's orbiting the sun? No. Like, imagine something you hate and somebody added math to it. That's not going to make me excited, right? So, yeah, nobody believed this still. Because technically, nobody really understood it in a way that there wasn't really absolute proof yet of all of this. It wasn't till the next person on our list came along that somebody finally had proof.